So before I define what an affine set is, let's first talk about what an affine combination is. So an affine combination is nothing other than a point in space x which belongs to a line. So in other words, if this line has 2 points, I can create an affine combination of those 2 points which results in this black line. So in other words, I can write it as follows. It's all x's, it's all points x, which are equal to alpha x1 plus 1 minus alpha x2. Whether you're in 2 dimensions, 1 dimensions, n dimensions, it's regardless of the number of dimensions of x. And not just that, one might think that alpha is restricted between 0 and 1, as we talked in previous lecture. Well, in an affine combination, your alpha could span all R. So when alpha is 0, you're at x2, and when alpha is 1, you're at x1, and when alpha is between 0 and 1, you're between x1 and x2, and in particular, when alpha is 0.5, you're somewhere at the midpoint, right? Now when alpha is negative, you're to the right of x2, and when alpha is greater than 1, you're to the left of x1, right? So yeah, an affine combination of 2 points is nothing other than a line joining those 2 points. Now, what is an affine set? Now that we know what an affine combination is, we can define what an affine set is. So an affine set is a set such that if you grab any 2 points, it is such that any affine combination of x1, x2 falls within this set. So for any x1, x2 in S, right? The affine combination of x1 and x2 is again in S. So all points x is equal to alpha x1 plus 1 minus alpha x2 is again in S for any alpha in R. So what this basically means is that, so you cannot draw this set as closed. It's not closed. We just said this affine combination is nothing other than this line up here. So this set should contain all points on the line joining x1 and x2. The infinite line, of course. So something that is not an affine set is simply if we're in, R square, for example. So we have this xy axis. If I close something like this, of course, it's not an affine set. Because, let's say I grab this point and this point for no reason, just to grab 2 points. Well, this straight line, this affine combination of those 2 points right here, i.e. the straight line, does not belong to this set, simply because it's outside the borders of the square, right? Therefore, we found a counterexample of 2 points such that their affine combination is not within the set, and therefore we conclude that the square set right here is not an affine set. Now, you can prove that the space R square is indeed an affine set, because grab any 2 points in R square, let a line pass through those 2 points, then any point on this line is in R square, because if x1 is in R square and x2 is in R square, and you just scale those 2 points and add them, again, you're going to end up with a number in R square, not in R cube. You're not going to add an entry, and you're not going to be somewhere, I don't know, it's in a complex set. No, if you add 2 numbers, they're indeed in R. But there is a formal proof for that, okay? I'm not going to prove it here. So this is not affine. R square is affine. We discussed it geometrically. And 3, an example of an affine set is all x's such that it solves the linear equation or the linear system ax is equal to b, right? So, let me just give you a small example so that you see what's going on. Why is this an affine set? So simply, so this is my S, right? Using the definition, let's pick any 2 points that belong to S. x1 and x2 are any 2 points that are in S without any, preference of what x1 and x2 are, but they're any 2 points. We don't care what they are, but we care that they're in the set, right? So if they're in the set, then both of them should solve ax is equal to b. Now the question is x is equal to alpha x1 plus 1 minus alpha x2 again in S? Let's call it x naught, right? So another way of asking this question is ax0 equal to b? Let's find out. So ax0, just plug in its affine combination, which is alpha x1 plus 1 minus alpha x2, which is alpha ax1, because alpha is a scalar, and oh yeah, we forgot something really important, even though it might sound dumb, but alpha is an R, okay? So alpha ax1 plus, again, 1 minus alpha is a scalar, so it's extracted, ax2. And what can we say about ax1? It's b. And what can we say about ax2? It's also b. So this guy right here is equal to alpha b plus 1 minus alpha b. Now you can expand this term right here to be b minus alpha b, and it will cancel with this alpha b right here. You end up with b. So what do we conclude? We conclude that this is true, which means that x0 solves ax is equal to b, which also means that x0 indeed belongs to S. Therefore, this set S is closed under affine combinations. So you pick any 2 points, x1, x2 in S. It turns out that their affine combination falls again in S. This means that any solution set of linear systems or systems of linear equations is affine. I remember this example. You know, in algebra sometimes, this is not, well, this is, linear algebra, but in algebra sometimes you have some examples which may sound stupid, but they're not stupid and trivial at all, okay? So let's say you're given just a set of 1 point x. That's it. That's your set. It's 1 point, a singleton. It has one element. Its cardinality is equal to 1, right? Is this set affine? So let's pick any 2 points in S. And you might say, oh, what do you mean any 2 points? But I have only 1 point. Well, you just pick it, right? So anyways, we can go back to this example right here, example 3, which is for solution sets, right? Is X a solution set to something? Well, yes, it is. It solves ax is equal to b, where you can choose your a and b, right? So if we choose my a is equal to I, the identity matrix, and I choose my b is equal to x, then this set is a particular instance of this set, right? I mean, we can see example 4 as a special case of example 3, right? So this means that example 4 is also an affine set. And you can also prove it using the definition. I'll leave that to you. Okay, so that's basically it for affine sets. Okay, now let's talk about convex sets, right? But as we did before with affine sets, let's define what a convex combination is so that we talk about convex sets. So a convex combination is an affine combination, but here we restrict alpha. So in this case, alpha is only bounded between 0 and 1. We had this figure when we were talking about affine sets. So right here, how a convex combination looks like is something like this. So we shrink the line. So it's a line segment, if you will. It's no longer an infinite line. It's bounded between x1 and x2. So x1 and x2 are also known as the endpoints. Therefore, a convex combination is all x's of the form alpha x1 plus 1 minus alpha x2, where alpha is no longer in all r, it's only between 0 and 1, right? This is a convex combination. So when do we say a set S is a convex set? So it's the same thing as affine sets, it's the same notion, but instead of saying it's closed under affine combinations, we say that it is closed under convex combinations, right? So you could see a convex set as an affine set with boundaries, right? It's closed so that it's, you have this line segment instead of an infinite line. So the way you can define a convex set is if you grab any 2 points, x1 and x2 in S, their convex combination should fall again in S. So any point of the form alpha x1 plus 1 minus alpha x2 should also fall again in S. But be careful, alpha is between 0 and 1. If alpha is an R, if you prove this for all R, then S is affine. Now, a nice geometrical way of seeing this is the following. So let me just draw some shapes right here. I'll draw a square. So that's a perfect square. And let's say I have a circle. Got a triangle. I have a C-shaped set, which looks something like this. What else? Let's put a donut. So a nice way of seeing a convex set, first of all, of course, it's they're allowed to be closed, unlike affine sets, which span infinitely, right? A nice way of seeing it is if you grab any 2 points and the line joining them falls outside the space defined by the closed shape, then it's no longer convex. So let me just go to the croissant real quick. So you've got those 2 points, okay. The line joining them falls inside the croissant. But if I grab those 2 points, 2 endpoints at the tip, and I join them with a straight line, you've got this portion of the line right here falls outside the croissant. Therefore, this set is said to be non-convex. It's a non-convex set. It suffices to find only 2 points such that a portion of the line segment joining those 2 points falls outside the set. Now we can say the same thing for the donut, right? So the donut, if I grab a point here and a point here, then this line has this portion right here outside the donut, right? So this, set is no longer said to be convex. On the other hand, the square and the circle, even the triangle, you are guaranteed that for any 2 points you grab inside, the line segment joining those 2 points will always be contained inside the set. Therefore, the square, the circle, and the triangle sets, there's no such thing as a square, circle, and triangle set, but you can define a set in a way that it looks like a square, it looks like a circle, it looks like a triangle, it looks like a croissant, or it looks like a donut, right? What you see in front of you is 2D, and it could be easily extended to 3D, 4D, and so forth. So yeah, those 3 sets right here are convex. However, those 2 are not convex. To define a convex set, we said that a convex combination is, the following combination between 2 points. But you can also generalize that. When you see convex combination in the literature, it doesn't only indicate that it's a combination for 2 points. It also applies to multiple points. So given endpoints x1 up till xn, they're also in Rm, then a convex combination is alpha 1 x1 plus alpha 2 x2 all the way down to alpha n xn. But here to grab the notion that, this set is closed, like we said before. When I say closed, I don't mean a closed set, no. I mean it admits endpoints, right? So to grab this notion, all your alphas should sum up to 1. Now that we defined what a convex set is, then we can now define what a convex hull is. So a convex hull, which is also denoted as conv of a set S, it's an operator. It takes a set and it will return something. What will it return? It's also going to return a set, but which set? It's a set of all convex combinations of points in the set S. So what we mean by that is, let's say I have the following set, the donut, again with the donut. And let's say I grab those 2 points right here. The donut is not a convex set. But what the convex hull does is that it convexifies it, right, informally. So it transforms it to the closest shape, which is convex. And what is that shape? It's the circle right here. And why is that? Well, let's use the definition. What did I just say that a convex hull of a set means? It is the set of all convex combinations of points in S. So it's not just any 2 points, you draw the convex combination between them. No, it's convex combinations of as many points as you want in S, right? What does that mean? So let's draw the donut again. Back to the donut example. So this is my donut, and I'll zoom in. As we said, the donut is not a convex set, but its convex hull is of course a convex set. As a matter of fact, a convex hull of any set is a convex set. So to see that, using the definition, it is the set of all convex combinations of points in the set S, right? So in other words, if I grab any 2 points, it is the set that contains the convex combination of those 2 points. So in other words, it will contain this line. And let's grab another 2 points. So if you do that for all convex combinations, which are infinite, and all points, which is also infinite, you will end up with the circle that exactly closes the donut. All this. You will end up with all this circle, including this gap, because those lines right here are within the gap. So if you do that infinitely many times, you will close this gap eventually, right? So yeah, that green set is the convex hull of S. So you can also show that a convex hull of, a square, which is already convex, is the square itself. So if this is my S, you can prove that the convex hull of S is again S, and the convex hull of a convex set is again the convex. Okay, now let's talk about what a convex cone is. We talked about convex sets, affine sets, convex hulls. Now let's see what a convex cone is. But before we do that, we need to define, as we defined for convex sets and affine sets, we need to define a similar type of combination for convex cone. And it's called the Conic Combination. In other references, it might be called a non-negative combination. Also, it could be generalized to multiple points, but for simplicity, let's grab any 2 points and multiply each one with an alpha 1, alpha 2, and add them. So it's, as you can see, a linear combination where the weights, alpha 1 and alpha 2, is non-negative. So it's greater than or equal to 0. So from the name non-negative, it means that the weights are non-negative. So you can see this is an affine combination. Affine alphas are in R, and they add up to 1, right? Well, in this case, they're not allowed to be negative. So yeah, this is what a conic combination is. So how it looks geometrically is as follows. It really has a nice interpretation. Really, you have to know something here, that this combination should contain 0. Simply take alpha 1 and alpha 2 to be both zeros. So you're in 0. So let's put the 0 here. So if I put my x1 right here and my x2, let's say somewhere here. They could be anywhere, but I'm just like putting them here. So let me just connect 0 with x1 and 0 with x2. So those 2 lines should look something like this, right? Now take the extreme case when alpha 2 is 0, right? This means that you will lie on a line which is of the form alpha 1, x1. Which means that it is the line connecting 0, the origin, with x1. This line right here is the case where alpha 2 is, 0. And similarly, this line right here is the case where alpha 1 is 0. Now, when alpha 2 is 0, i.e. we are on the green line, this is for all alpha 1 positive, because if alpha 1 is negative, you would end up below the origin, right? So you're on this green line. Similarly, when alpha 1 is 0 but alpha 2 is positive, you're on the blue line. And anywhere in between, you will end up in the red region. So yeah, this is how the conic combination looks like. It's a cone. Simple as that. So your x's are going to fall here. It will, walk around in this cone section. Now, with that being said, defining what a conic combination is, now we can define what a convex cone means. So a convex cone is nothing other than a set that contains all conic combinations of points in the set. So if I had this shape right here and I had any 2 points, if I grab any 2 points, then it should be, and the origin is here, 0, then the convex cone should contain all points, not only, but should contain all such points. right? And even up to infinity. Now, you do this for all 2 points right here, and you would contain something like a projector, like a cone that would exactly contain your shape. This is so cool. So if you do this for those 2 points right here, and you join them with the origin, you would also contain a larger region, which is the blue region. Now grab endpoints, you can grab the endpoints to see how it looks like maximally, and you would see that it would contain the green region, all this shape, right? So it's like a projector projecting onto your set, not to be mixed up with projector in linear algebra, because in linear algebra, projector means, you're projecting onto subspaces, and it's another space that spans the subspace. I'm not talking about a projector in terms of subspaces. I'm talking about a projector as in, how a real projector in real life would look like. Now let's define what a hyperplane is. So a hyperplane is a set, it's defined as all x's, that satisfy the following. A transpose x is equal to b. So b is a scalar, and a and x are vectors, or points in n dimensions. In that case, we define an inner product, so they're vectors. Now, if you would expand this, it will look something like this. Sum of ai, xi is equal to b. If the space is n-dimensional, then I would go from 1 till n. And how a hyperplane looks like is a line in n dimensions, so something like this. Not just any line, so given A, given B, A is seen as a normal vector. My A vector would look something like this. If I'm given a point, x naught here, and B, it defines the level of the line. So if I'm in 2D, the greater B is, then this would be lifted up. If, let's say, if this is for B is equal to 2, then the line for B equal to 3 would be somewhere parallel, because they would both be sharing the same normal vector. But, because B is greater, then it should be lifted upwards. Similarly, if B is less than 2, then it should be somewhere here. Again, parallel, right? Because it would also be sharing the same normal vector A. So what I mean to say is that, B would only define the level, how high or low my line is. Okay, so yeah, those lines define something called a hyperplane. It is a plane in n dimensions. It's not just a line, it's a plane. So this is in 2D. If I were to, pop one more dimension right here, this would look something like this. And thus the name hyperplane. They all share the same normal vector, which is A, right? Okay, each one of those planes, 3 planes, is called a hyperplane. Now, what is a half space? Well, the half space is nothing other than you just replace the equality with an inequality in the definition of a hyperplane. So instead of saying A transpose is B, define it to be less than B. In other words, if B is 2 right here and A is given, it's all the planes, all the hyperplanes below B is equal to 2. It's all the hyperplanes below this red hyperplane right here. So it's the black region, if you will. It's everything below this plane right here. So it cuts your space into 2 spaces. The space that you want, which is the half space, and its complement. And all this is defined for A is not 0. So all this we talk about when A is not 0. You can also prove that hyperplanes are affine using the definition we talked about in affine sets. So it's affine and convex. It's both affine and convex. However, half spaces are only convex. So as an exercise, you can use the definitions as we showed in examples previously and prove that a hyperplane is both affine and convex, and a half space is convex. One way of doing that is, you pick 2 points. Let's say we're proving a half space is convex. Just pick 2 points in the half space, so x1 and x2, such that when you transpose them with A, they're both less than B. And if you would form a convex combination, you should prove that it's also less than B, given that this guy right here is less than B, and this guy right here is less than B. Right, so let's define another type of interesting set, right, which is called the Euclidean ball. So give me a center and give me a radius, and I can define what a ball is. Let's say my center is C. Again, it's in any dimension. This could be in n dimensions. A point in n dimensions, C, and a measure in R, a radius. So r is positive. Of course, you can't give me a negative radius. It's not allowed. And your c is in n dimensions, right? It's a vector. So it's all points in n dimensions such that their Euclidean distance or L2 distance is less than r. So if my r is this guy right here, it should be this ball right here. Now if it's in 3 dimensions, it's a sphere. It's in 4 dimensions, it's a, you know, a hypersphere maybe, if that works, and so on. So this is r, and it would be my region right here. You know, in optimization, it's really important to visualize stuff. It's super important. And also in linear algebra, and sometimes the answer lies in how the shape looks like, and sometimes not. So a rigorous way to define a Euclidean ball is a ball given the center and radius. So again, it's a set. It's all x's, given that the distance is simply less than or equal to r. In some other references, you might find an alternative definition which is sometimes more suitable. So it's all points such that you wiggle the center, right? You wiggle it by an amount of a scaling factor. You point towards, you know, you're at C, so you can wiggle around by a quantity of RU, where, you know, R is fixed, but U is a vector, right? But it's all used such that their Euclidean norm is less than or equal to 1. So in other words, maximally this, when U is equal to 1, you would be at the borders of the Euclidean ball. We're taking the extreme cases right now. When the norm of U is 0, you will be exactly at C. Okay, so that's what a Euclidean ball is. Okay, so now let's try to generalize the Euclidean ball. You could, you know, stretch and compress your Euclidean ball, and you end up with something called the ellipsoid. So give me a center C, and instead of giving me right now a radius R, you would give me a matrix, right? Instead of an R, you would give me a matrix. So you can also define an ellipsoid instead of a certain center and a radius. No, you need more information than a radius. You need a matrix P. And not just any matrix P. This matrix P should be able to measure. So matrices that are able to report measurements are symmetric positive definite matrices. So here P should belong in, you know, the set of symmetric positive definite matrices, which is usually denoted as S++. Now, why 2 pluses? If you put 1 plus, then you mean semi-positive matrices. So semi-positive matrix. And I'm not going to open a lesson on linear algebra, but I think whenever necessary, I'll just write down what that means. So I'll define right now here what a PSD, or a positive semi-definite matrix, is. So here you have one additional parameter. It defines the dimensions of your matrix, n by n. So it is such that all quantities x transpose AX are greater than or equal to 0 for all x in Rn. So this is a PSD, and a PD would be the same as PSD. So PD or S++. If A is in S++ of n, then X transpose AX. And if it's always positive, then it's PD. Now one might tell me, oh, but wait a second. Okay, go on. But what if I choose a vector, it is positive, and I choose another vector, and the same quantity is negative? Well, it's no longer PD or PSD. Simple as that. It's actually neither, okay? Now, another question could be, but wait, what if it's always negative? Well, you have the same definition, but you could say a negative definite or a negative semi-definite, right? But usually people talk about positive because if you insert a minus right here, you could flip it to a negative. So all stuff that apply to positive definite apply to negative definite. Just insert a minus, right? Anyways, we're concerned with this matrix right here, S++ of n, and this would report how tall or how fat my ellipsoid is. If I were to write this down as a set, it's all x's such that x minus c transpose p inverse x minus c is less than or equal to 1. It will look something like, you know, this. This is a weird looking ellipse. It looks like a peanut to me. Anyways, P would define, you know, this measure right here in one of its entries, and this measure right here. And it would also define the rotation. And a natural question here is, yeah, we have an inverse here. What if I give you a non-invertible P? Well, you cannot do that for the class of positive definite matrices. So all positive definite matrices are ensured to be invertible. That's one of its properties. So you could also represent your ellipsoid as we did in Euclidean ball, but instead of, putting this P right here, you could wiggle around your center. So it's a C plus some wiggling term of the form. It's not an RU like we did. No, there is no R here. It should be a matrix. It's not P. It's not the same P. It's another matrix. So let's say it's a Q. But this Q should also be invertible. And again, your U in Euclidean norm is bounded by 1. Since we talked about norms, I think it's really important to define what a norm is. So a norm, which is usually denoted as two pipelines on the left and right, is nothing other than a function that takes you from Rn and it returns a certain measure, a real number, which is indeed positive. It's a measure, so it should be positive. Or, non-negative. It could be 0. Now, any norm satisfies 3 properties. So the first property is the 0 vector, 0. And what does it say? It says that if your norm is 0, then your vector has to be the 0 vector. So if you ever encounter a 0 norm, that's property number 1. And property number 2 is the scaling property. So if you scale any norm, alpha x, where alpha is a number, x is always a vector, this is equal to, alpha could be extracted or factored outside. But it is factored outside an absolute value because your norm always returns a positive number. So since the norm is positive, your alpha, let's say accidentally or not accidentally, let's say you set alpha as -2, then if alpha is extractable, if you can extract it, you should at least extract it in the positive sense. You can't say it's -2 times something positive, which is negative, which ruins the definition. No, we have to maintain the positivity or the non-negativity of the norm. That's property number 2. And the last property is triangular inequality, which is the norm of adding 2 vectors is always less than the sum of the norms. So the norm of the sums is less than the sum of the norms. Okay? Of course, we can define countless number of norms. Just grab a function that takes as input or as argument any vector of any size and returns something positive with those 3 properties, and voila. Examples on norms is, as we saw before, the Euclidean or L2 norm, which is defined as the square root of the sum of squares of the entries of x. If I take the L2 norm of following vector, which is 3 and 4, it is the square root of 3 squared plus 4 squared. Okay, let's say you were given this function without being said it's an L2 norm. You were asked to prove that it is a norm. You can easily prove those 3 properties. So when this is 0, the sum of positive numbers is 0 when, each and every entry is 0, right? And also when you scale this guy with an alpha, then each entry here is alpha xi squared. Then this alpha is extracted outside the square root by an absolute value, therefore proving the second property. And the third property, I will leave it to you. If you have any question, you can just hit me an email. I'll leave my email in the description. So yeah, that should cover all norms, right? But why are we talking about norms? It turns out that you can define a lot of sets using norms which are convex. As we saw previously in ellipsoids were defined using norms. This is also a norm, even though you do not see those fancy pipelines. Given positive definite matrix P and a center C, you can define the following norm. It turns out that this norm, if you define this norm and restrict it by 1, then this set is easily proved to be convex. You can see it geometrically. Take any 2 points, join them with a line segment. The line segment will always fall inside the ellipsoid. Also, going back to the Euclidean ball, we also defined it with the Euclidean norm, the L2 norm. Take any 2 points inside the Euclidean ball, it will always fall inside the Euclidean ball. This is where norms are used in convex sets. So you can define many shapes, many sets that turn out to be convex. Another simple example of a convex set using norms is a norm cone. It's a cone, a normal cone. So if I draw a cone in 3D, so you can define it using sets as follows. So a norm cone is all x's such that your Euclidean norm is less than a certain level alpha. Or let's call it, a radius, because it makes more sense. So, given an r, let's take any circle centered at 0. So this is a circle with radius r, and this is another circle with radius less than r, and so on. So you're defining a cone. Again, this cone is convex. You take any 2 points inside, a convex combination would, again, fall inside this set. Okay, let's talk about polyhedra, which is another type of convex set. So a polyhedra is nothing other than an intersection of hyperplanes and half spaces. So hyperplanes are solutions to systems of linear equations. This means that we can define them as ax is equal to b. So each hyperplane is an inner product. So if we look at each equation here, if we zoom in at each row of this equation ax, it looks something like this. So if I take a look at the kth row, it would look something like ak transpose times x is equal to bk, where ak is the kth row of A and bk is the kth element of B. So going back to half spaces, it has the same form, right? So this means that when we have multiple equations of A transpose X is equal to B, k is going from 1 till n, I don't know, depends on the size of the matrix A. So let's say A is in R n by m. This means we have n equations of this form. So we should satisfy them all with equality, means that it's the intersection of all such. So if we have all this system, it means that the resulting solution set is nothing other than the intersection of all such equations. So let's say my first hyperplane looks like this, where a1 is the normal vector, and this is the other one, a2. I have another one here, which is a3, and so on. You get the point. Now, it could be opened and it could be closed. It depends really on how my A1 and A2 and A3 are pointing, all my AKs are pointing out, right? You're just on the border here, right? It's just a border thing. It could also be in the interior, which means that we have other types of equations as such. Cx is less than D. Now, what does that mean? If C is a matrix and D is a vector and X is a vector, it means that component-wise, if I look at the kth, entry of Cx, so the kth row or entry would look exactly like this. So ck transpose times x, and you'd have a dk, right? But instead of an equality, you have an inequality. Now, we have to do a really important distinction between this and another type of equality, which means semi-definite, right? So you find also in references that I have a matrix less than another matrix. That does not mean that it is component-wise, the kijth entry of A is component-wise less than the ijth entry of B. No, it means that the matrix B minus A is positive definite, okay? Well, in this notation, we don't mean the positive definite inequality. No, we mean component-wise, okay? So this thing right here means component-wise. Okay, good. So if k goes from 1 till, let's say, I don't know, it doesn't necessarily have to be till n. It could be another thing, let's say L, right? Where C belongs, let's say, to R L by M. This has to be M because if we're talking about the same X here, then it has to have M entries. So that being said, if we want to, draw Cx less than D, it's the same thing. You have those hyperplanes C1, C2, C3, all the way to CL, right? And in that case, it would be, the interior, because it will be defined as the half space, right? So it's everything to the bottom. It would be something like that. So the interior. On the other hand, here we were walking on the borders, right? Because it's equality. So we are really on the borders. Now, a polyhedra is the intersection of possibly ax equal b and cx less than d, right? So it could be a mix of both. So a polyhedra, again, is another example of a convex set. And the way usually people prove this is using the definition, right? You take any 2 points and then you prove that a convex combination of those 2 points falls again inside the set. There's another smart way of proving it, is using the fact that the intersection of convex sets is again convex, okay? So what do we mean by that? We know that hyperplanes and half spaces are convex. You can easily prove that. Well, a hyperplane is a line. Any 2 points you take on the line, any convex combination of a 2 points you take on a line is again convex. You can prove it by the definition and you can see it geometrically, right? And a half space, which falls beneath a hyperplane, is also convex. Again, you could prove it by taking 2 points and the convex combination of those 2 points is again inside the half space, or you can prove it using the definition, right? As we said, using the definition again, the polyhedra is nothing other than the intersection of a bunch of hyperplanes and half spaces. So it has to be convex because there is a property we will see later on. The intersection of convex sets is again convex. Okay, so let's talk about positive semi-definite cones. So first of all, we need to define some notation such as S superscript n. Now, what does that mean? First of all, when you encounter such a notation in many books, this most probably means that it's the set of all symmetric n by n matrices. And how people usually denote it mathematically is as follows. So Sn is, let's translate this mathematically. So it's all matrices that are of size n by n such that X transpose is X. That completes the definition, right? So that's the first notation we need. And the second one is we're going to add something to, all symmetric matrices. We're going to add a plus as a subscript. That means that it's the set of Sn, which is the set of all symmetric n by n matrices, plus positive semi-definite. So it's not only symmetric matrices of size n by n, it's also, you add to that the fact that those matrices should also be positive semi-definite. So mathematically, it means that we could write this, right? Because we already defined what Sn means. It's all symmetric matrices such that Z transpose XZ is positive or equal to 0 because we have the semi, right? Now we'll see a positive definite what it means for all Z. And one more thing, we have Sn subscript double plus, which means it's a matrix that belongs to Sn and it's positive definite. So mathematically what that means is that it's again a matrix in Sn. It's a symmetric matrix of size n by n such that Z transpose XZ is strictly positive for all Z in Rn. Okay, good. Now we define 3 basic notations, Sn, Sn plus, and Sn double plus. Well, how are we going to use it here? Let's set n is equal to 2 first of all, and let's consider Sn plus. So all positive semi-definite symmetric matrices, which in that case would be S2 plus because n is 2. So those matrices would look something like this. Let's take an x in S2 plus. So I could express x as, first of all, x, y on the sides, and z right here. Y on the sides because it's symmetric. And where does the positive semi-definite property come in place here? It's that this matrix, you have alternative properties to this. One of which all eigenvalues are positive, right? Or equal to 0. and you have the leading minors, which are also positive definite. So in that case, x and z should be positive, right? So yeah, the question here is how many variables did it take me to define x? It took me 3 variables, x, y, and z. So here, what I can do is, I could plot how x, y, and z behave, right? Now, I'm not going to plot it here because it's not fun. Let's plot it on MATLAB, okay? Right, so I've got MATLAB in front of me, and it's okay if you don't know MATLAB. I'm just going to plot this guy right here, okay? So for those of you who don't know what MATLAB is, it's not a programming language. It's not, because I hear a lot, I encounter that a lot. Do you program on MATLAB? Well, no, I don't, because MATLAB is not a programming language, right? So what MATLAB is it's made for the community of engineers and mathematicians, physicians, and all these kind of people that are into science, oriented more towards science and math and these kind of stuff, not oriented towards programming. Those people that do not know how to program on C and C++ or any other low-level programming language, and also that do not have the time, because if one line of MATLAB code right here is a bunch of a lot of routines and functions and C being called, and because the low-level MATLAB is based on C and C++. So all these functions like eig. So what is eig? Eig is so help eig. Eig is, here's the manual. It computes. You give it a matrix A, and it returns the eigenvalues and eigenvectors of A. So imagine how much code you need to write in C and C++, right? So MATLAB is made for mathematical computations and other, there's a lot of toolboxes. So you've got toolboxes in statistics and signal processing, finance, physics, everywhere, machine learning, and usually there's a lot of, repetitive stuff done in each of those toolboxes, each of those domains, right? So instead of you having to come and code them from scratch, you've got them already there for you. They're just there for you to use, right? So that saves a lot of time. Okay, enough talking about MATLAB. Let's plot how a PSD cone looks like in 2D. So n is 2, right? And okay, so if we go back here, we've got x, y, and z, right? So x is here, z is here, and y is here, right? So we've got this x, y, z matrix here. So let's define a range for x and y, right? So let's say you'd like to plot x from 0 to 1, right? Now, since, in computer, nothing is continuous, you need to discretize your vectors. So I'll take steps of 0.1, or we'll see how that would look like. And I'll take y the same as x. So both x and y contain values from 0 to 1 discretized at 0.1 steps. So I just defined my x and y vectors. Now I need to see how z will behave given that uppercase X is a PSD. Let me do something in MATLAB. So this is my x-axis and this is my y-axis, and I'll call something called a mesh grid. Okay, I'm just going to go back here a bit and, I'll erase my z here and my y here and just replace y with z, right? I'll put a z here, and a y here. I didn't do anything, superficial. I just denoted y instead of z and vice versa. What are the conditions so that the matrix X belongs to S2 plus, right? So what are the conditions that X is positive semi-definite? So one property, as we mentioned, is that all principal minors should be positive, right? So what is a principal minor? It is all determinants obtained by deleting any k rows and k columns. So first start by deleting the second column here and the second row here, right? Therefore, we have only element x. Therefore, the first condition is that the first principal minor is positive, which is x. So x has to be positive. Now there's another principal minor which is obtained by deleting nothing. So with that being said, we need that the determinant of x is positive. So what is the determinant of x? It's this guy times this guy minus this guy times this guy, right? It's xy minus z squared, which is positive, right? In other words, we require that xy is greater than or equal to z squared. In other words, we also require that this, which means that the square root of xy is greater than or equal to z, right? This should be plus or minus, because once you do square roots, you're going to have a plus or minus appearing, right? So yeah. So x positive means that if I want to look at it in 3D, if this is my x-axis and this is my y-axis and this is my z-axis, I'll be only looking in this half space right here. What is right here? If this is the yz plane, I'll be looking to everything pointing towards x, right? In the positive sense. So that's one. And two, since I have a square root right here, and since my x is positive, my y is not allowed to be negative. If y is negative, then everything inside the square root is negative. And therefore, square root doesn't work with negative numbers, so you should omit this option. Both of those mean that y is also positive, which means that we're also looking in this sense. Okay, so x is positive and y is positive. Now let's go back to MATLAB and impose those conditions and then plot and see how the plot would look like, right? So let's see how z equal to root xy would look like. So the x-axis times the y-axis. How do we plot that? So if I remember correctly, I have x-axis, then the y-axis, then z, something like that. So let's give it a run. Okay, it looks something like this, but it's not really discretized properly. You see those grids, right? This is because I've got 0.1 steps. Now let me increase the number of steps. Okay, it looks smoother. Okay, this is one part of it, right? Because as we said right here, we've got the plus and we've got the minus, right? So we have to also plot the negative part of it, right? So a quick trick over here would be something like this. So I could surf again, x-axis, y-axis, and minus z. Yeah, that looks good. Why not? Looks something like this. It's curved on the edges. Looks like a paper plane. Let's go even further with the limits till 2 on x and y. Yeah, it looks something like this, exactly. Yeah, so this is the positive part over here when we said that, z is less than the square root of xy, and the one below here is the negative part. So if I extend it, this is how it looks like. So that's why it's called a cone, right? It's not any cone, it's a positive semi-definite cone. It's a bent cone. It looks like those, I don't know if you've been in Belgium, but in Belgium they sell those fries that are, that are fried twice. So Belgium is known for their fries. And the fries are put inside something like this. Or if you've been in Spain and you've had some churros, I don't know if you know what churros is, but it's a really popular thing in Spain. So churros are usually put in stuff like those. Also, if you come from Turkey or Greece, they put something like a kebab inside something what looks like this. So, every time you're eating churros or kebab or I don't know what, you should remember the PSD cone, right? So this is how it looks like. In case you're lost, I'm lost, but in case you're lost as well, like me, you're mixed up where the x, y, and z axes are. Let me label them right here. So my is x-axis. We can label them on MATLAB as follows. There you have the figure. So this is the x-axis, y-axis, and z-axis, right? Okay, looks good. Yeah, so if you want a brighter color, this is how it looks like with less steps. This is how it should look like. Good. So yeah, that's about it for PSD cones, right? So now we're going to discuss operations that preserve convexity. So you have a set C. C is convex. What kind of operations can I do on C so that it remains convex? Or multiple C's. Let's say I have multiple sets, right? What operations could I do on those multiple sets so that the resulting set is again convex? So many times in research, or when you're proving something, you'd like to go to the definition. So if C is convex, as we saw previously, this means that for any x1, x2, and c and theta between 0 and 1, we have that the convex combination of x1, x2 is again in C, right? This means that C is convex. Okay, good. Now we're going to talk about some operations that preserve convexity. And it turns out that it's easier that you notice those properties in practice rather than having to prove, the resulting set again from the definition. So what do I mean? I mean that let's start with intersection. And we saw that previously when we talked about polyhedra. So over here, when we said that a polyhedra is a set that solves a system of linear equations or linear inequalities. Now you can prove that the intersection of all those solutions is convex, that the resulting set is convex, right? You can prove it from the definition, and it's easily done. There's no doubt about it. But it will take a bit more time, Instead, you can use smaller pieces of information which are much easier. You can prove that each resulting set from these equations is convex. So hyperplanes are the ones with equality, inner products with equality. The half spaces are ones with inequality, right? So if we know that this guy right here, the set generating this guy right here, and this guy right here are both convex, then you're done. A polyhedra is convex, period, right? So now we're going to see, so yeah, this has a proof. You can actually prove that if CK is convex for all k going from 1 till n, then the intersection of all those convex sets is also what? Convex. So how do we prove that? Okay, so what do? We assume that the hypothesis is true, and we do some input. Go down to see how the intersection is convex. Let's prove this by definition. So this set right here, let's call it, I don't know, S if you want. So let S be the intersection. We're going to assume that all the CKs are convex by hypothesis. Okay, now let's pick 2 points, x, y, and S. And also let theta between 0 and 1. Now let's take the convex combination of x and y, meaning that let's consider the point theta x plus 1 minus theta y, right? So let's see what that means. Since x is in S and y is in S, what does that mean if x is in S? It means it's in the intersection of the CKs, right? So let's consider only one CK. Let's call it CK0, right? So let K0 be any integer between 1 and n, right? And let's consider the set CK0. So CK0 is one of the sets C1 till CK, still Cn. This means that x is in CK0, right? Because x is in C1, x is in C2 till Cn, right? It's in the intersection, means that it belongs to all of them. Similarly, y is also in CK0, and we know that CK0 is convex because all the CKs are convex. What do those three mean? It means that by definition, theta x plus 1 minus theta y, by definition of convexity, this guy will fall again in CK0. Now let K0 go from 1 till n, means that this convex combination will fall each time in C1, C2 till Cn. What does that mean? Since it falls in C1 up and C2 up till Cn, it means that simply this point will fall in the intersection of all the CKs, which is the set S, and the proof is done. So we proved it by the definition. You could really create a lot of geometric examples like the following. So let's say I'm in the XY plane, keep it 2D, and let's say I'm given a circle. So you could really grab any multiple combination of all the sets that have been mentioned. I'm going to grab a circle, even though I didn't mention it. Oh yes, we did right here, right? So circle is convex. So yeah, let's grab a circle which is convex, and let's pass, a hyperplane, and take the space below it. So the half space. So this set right here. So the black set and the blue set. So their intersection, which is the green set, is again convex. It's easy to prove it geometrically. Take any 2 points, pass a line. Each point on the line should be inside the green space. So we're going to take 2 points and pass a line, the convex combination. So all the line falls inside the green space. This means that the green intersection is again convex, okay? This applies also to multiple sets, many countable sets, and yeah, that's it. And really, it turns out that many hard sets to comprehend. I could like right now put a set in front of you. I could put a really hard set in front of you, but you can prove it. You can really prove it using this intersection property. So I can put this set in front of you, which looks really, if you don't know this property, you're going to have a hard time proving it. So the following set, so a vector of size n, such that, okay, here's where it's going to, look dirty. So the sum of xk cosine kt. So if you take all this sum and take the absolute value of this sum and you say it's less than 1. And we need one more thing, which is, what is it? I think it's the absolute value of t being less than, it should be less than pi over 3. So it turns out that, by the way, this set has implications in control theory. So when you say a quantity like this is bounded, there's some cool stuff you can say about x. Something about controllability, and by the way, this sum also appears in Fourier series. So when you're doing Fourier analysis for periodic functions, and it's like Taylor's series, but you're writing it in a sine cosine basis. So instead of expanding in polynomial basis, you would expand in a trigonometric basis, right? And this applies to periodic functions. So periodic functions appear a lot in control theory and signal processing, and this guy right here actually means something in this domain. It means that you can control it with some, we're not going to go in that domain right now. We're going to keep stuff mathematics. We're talking about optimization here. So yeah, this set S, you could prove it's convex using the definition. I don't know how hard and easy it is because it looks hard. So if you take, not going to lie to you, but if you take, 2 points x and y in S, and you say, oh, let's take the convex combination theta x plus 1 minus theta y, where theta is between 0 and 1. So what does that mean? What does this tell us? As you can see, it's not that easy. So how are you going to go from saying something like the sum of xk cosine kt less than 1 and the same quantity for y cosine kt less than 1 to something like this? The sum of theta xk plus 1 minus theta yk all multiplied by, cosine kt less than 1. How are you going to go from those two to that? That's the, the challenge right here. Also, again, given that t is less than pi over 3. It's not that straightforward, huh? It's not that straightforward. This is not an easy thing to do, but it's really easy to prove it using intersection. I'm not going to do it here, but you can see that this is an intersection of convex sets. Okay, so that's it for intersection of convex sets. Now let's talk about another type of operation that you can do between convex sets and the result turns out to be convex. So we're going to talk about affine transformations. Now with that being said, what is an affine function first of all? So we need to define something called an affine function. Well, it's a function that goes from n dimensions towards m dimensions, right? So it takes a vector x of size n and it returns a vector of size m. Okay, so there's infinitely many transformations of such types or functions of such types, but when we talk about affine, we mean those of the following form. So they're completely linear, ax plus b, where a is a matrix and b is a vector. This means that a is of size, since we're taking a vector of size n and we're returning a vector of size m, so A has to be of size m by n, right? Similarly, B has to be of size m. Well, how does that apply to sets? Well, simply we can define for a set S another corresponding set which is f of s. And what does that mean? It means they're all vectors of the following form where x belongs to S, right? So give me a vector from S and I'll transform it to a vector in f of s, right? You just apply this type of transformation, f of x, where f of x is ax plus b. Now this f of x could be any f of x, right? It could be something that is highly nonlinear. But when it is of the form ax plus b, then we are sure that f of s is convex if s is convex. So this type of transformation, which is called an affine transformation, it's when f of x is ax plus b, preserves convexity. So when S is convex, we're sure that f of s is convex. Inversely, we can also say that the inverse image of a convex set is also convex. So if you're sure that f of s is convex, you could also say the same thing about s, okay? So it's like the other way around. So this means that we have equivalence in affine transformations, which means that if and only if, so double F means if and only if. So if and only if s is convex, then we can say f of s is also convex, right? Other notations would be something like this. S is convex, double arrow. F of s is convex, right? Usually there's a notation for this, or inverse image. So let's say this was denoted as, I don't know, let's say k, right? And how would you denote s in terms of k? Using the same notation, you could say that s would be, in that case, the inverse of k, right? Because that's what you're doing. You're going from f of s to s. Means that you're applying the inverse of f to go back to s, right? So you're saying that if k is convex, then so is the inverse image of k. That's what it basically says when you go from 2 to 1. You can easily prove that. We're not going to do that just for sake of time. So that's it for an affine transformation. That's all you need to know. There's another type of transformation that also preserves convexity, and it's called a perspective transformation. So as affine transformation, there's an affine function. Then here we should define something called a perspective function. And what is a perspective function? It's a function f that takes a vector of size, let's say n, and returns a vector of Rn minus 1. So a vector with one size less as output. But why is that? It's because this function is doing the following. So if f is taking as input a vector, so let's say x1, x2 up to xn minus 1 xn, so let's say this is the input of f, then the output is of the following form. It's x1 over xn, x2 over xn, down till xn minus 1 over xn. So what we're doing here is that we're grabbing the last element xn and we're dividing all the previous elements by xn. And the resulting vector would be one size less because xn is no longer there, right? If it were there, then you would see a 1. That's one way of defining a perspective function. And the domain of this function, or the DOM of f, it's all x in Rn such that the last entry, xn, this guy right here, should not be 0. And even more than that, we're going to tighten that up and say it's all xn's that are strictly positive. We don't want to allow negativity, switch of signs when we divide by xn due to its negativity. No. So yeah, this f is called a perspective function. And a perspective transformation is, given a set S, you transform it as follows. It's f of s where it's all f of x's such that x is in S. But this time f is defined as the perspective function, okay? So we could have called this f a p instead, right? So p here, p here. To avoid confusion with the affine, I'm just denoting it as p, dom of p, and p of x, p of s. That's basically it. So if s is convex, then so is p of s. Okay? Now indeed, p of s would be one dimension less, right? Because all p of x's would be in Rn minus 1, be one size less. In contrast to affine transformation where, you're going from one dimension n to another totally different dimension. So yeah, there's one more transformation I'd like to mention, which is the linear fractional transformation. And yes, we're going to define a linear transformation function. Let's call it L. And as affine, it goes from Rn to Rm. Right? From the name, we're going to encounter fractions, but this time not fractions for scalars, no, fractions for vectors. So x is a vector. How do we define that? Well, give me a matrix A and give me a vector. Also give me two more vectors, C and D, C transpose plus D scalar. Yeah, so this is a linear fractional function. A is, again, as affine, it's R m by n. And B is Rm, C is Rn, and D is nr. It's a scalar. Okay, good. Now the domain of this function, the domain of L, is all vectors in Rn such that the denominator is not 0, and even more than that, it's strictly positive. We're going to rule out all C transpose X plus D's that are strictly negative or equal to 0. Equal to 0 is obvious. Negative, just to keep stuff convex. If you want to really prove why such transformations keep the transformed set convex, you're going to need this piece of information somewhere in the proof. Now, as we did previously in affine and perspective transformations, we have a transformation here which is for each set S, there's a set L of S, which is defined as follows. So L of x's, where your x's belong to S, right? And again, if S is convex, so is L of S. It works also all the way around. So if L of S is convex, then so is S. So we saw three types of transformations that preserve convexity, which are affine. It's a linear transformation. We've got the perspective transformation, which is of course nonlinear, and the linear fractional transformation, which is of this form. It's a fraction. So all such transformations preserve convexity. Now, if S is not convex, what can we say about L of S? Could we say that it is not convex or inconclusive? Now, since this thing happens both ways, right? If S is convex, then so is L of S, and if L of S is convex, then so is S. So if you're going from a non-convex set, you're transforming a non-convex set, you can be sure that the transformed set is also non-convex. Okay, examples here could be you choose any A, any B, any C, any D, and you can make a lot of, counter examples with this. You could choose, let's say, for simplicity, let's say A is I, is the identity matrix, B is 0, C transpose is, let's keep it C, and let's choose D is 0. So L of X in that case would be I x plus 0 over C transpose X plus 0, which is I times X is X over C transpose X. And no, this does not cancel with this. You might do this mistake, but it's not. So as you can see, if you grab any vector, you do an inner product with X divided by X. And if X is coming from convex sets, then if you do this for all X's in that set, the resulting image, which is the set defined by L of S, is also convex. Now here you could really do a lot of examples. Like if you're working in n equal to 2, so X is of size 2, then if your C is chosen to be, I don't know, 1, 1, let's say, then this guy right here, given this X, you could write it as follows. So X in the numerator, there's nothing you can do about it. But in the denominator, you have 1, 1 multiplied by x1, x2, you get x over x1 plus x2. That means is that you will get another vector called L of x, where you're dividing x by the sum of its entries. And why is that special? It's because if you sum the entries of L of x, then you'd get 1. So that was one example, and that's all I have to say about operations that preserve convexity. Right, so now let's talk about some stuff you can actually do with convex sets. So the first and most important thing is generalized inequalities. What that means is that you can actually generalize the inequalities when you were working with scalars or numbers, like when you say 2 is greater than 1. This inequality you can even generalize it to matrices. And we even saw that when we said that the matrix A minus B is positive definite, we denote it as such. A is greater than B in a positive definite sense, right? Well, we're going to see where this comes from. Where does this, inequality come from? For each inequality, you should define, the set that where you're talking about. So with this inequality, with the inequality that it is defined in the space of real numbers, right? What that basically means is that you're comparing numbers that come from the real set, right? Well, where does this inequality come from? On which sets does it work? Well, let's define a set called S. How does the set where the quantities come to compare look like? This set should have some properties. We're going to enumerate them here. The first property that you should have is that S should be closed. What does closed mean? Geometrically, it would, contain its boundary. A small example is when you define a set in 2D, let's say a circle, and mathematically, if it's centered at 0, and this is my x and this is my y, everything inside the circle, mathematically, it's expressed as the following set. It's all couples x, y, such that x squared plus y squared is less than, the radius squared. Let's say it's a unit circle, so less than 1 squared, which is 1, right? Well, if you want this set to be closed, then it should contain the boundary. And the boundary is nothing other than the circle x squared plus y squared is equal to 1, right? So this guy right here should be included in that set S, right? Well, how do you express that mathematically? Well, you could just say I want this and this, or you could, say it's less than or equal, right? In that sense, you include the boundary. The set S is said to be closed. A really formal definition of closed is that its complement set is open, okay? And you can't think about open and closed sets as a binary thing. So if it's not open, it's closed, and if it's not closed, it's open. No, it's not like that, okay? Just for sake of clarity. There's a lot of counterexamples where, this is look, what I'm talking about right now is really topology. You go to topology, you study topology, and you see all sort of interesting stuff, I would say. Again, a set S could be both closed and open at the same time. Right, so a formal definition of closed would be that its complement set, let's say S superscript C, or you can also denote it as S bar. So the complement, everything which is not in S, it's all elements X that come from, if you're working in the field Rn, let's say. So it's all such X's that are in Rn, but that do not fall in S. Anyways, S is closed when this set right here, is open. And what does open mean? A set is said to be open if you can grab any point and find a certain number, which is the radius epsilon, right? Such that if you draw a circle of radius epsilon, then all points within this disk will fall in S. But wait, this happens, I can always make my radius small enough such that all points in the neighborhood of this point, which is x0, is contained in S. But that's not true because, let's say, again, your set is closed, and therefore the boundary is within S. So I can simply choose a point here, and I can draw a circle here. If you choose any epsilon, no matter how small, you can never fit all points within the circle to fall inside S. This portion right here is always going to fall outside S. This guy is good, whereas the blue portion fall outside S. So in that sense, you can think about it that way. So going back to the formal definition, so SC is open if, so this notation means for every x in SC, or let's call them x nod, neighborhood, so n of x0 means the neighborhood of x0 is again in SC. So what is the neighborhood? We defined it as a disk right here, right? So it's a disk of radius epsilon and center x0, which is a set, right? Which is all x's such that the Euclidean distance from x0 is less than epsilon. This is a disk. So yeah, this is what open means. If you want to write it in a more compact way, again, SC is equivalent to this. So SC is open if for every x0 in SC, you can give me an epsilon such that this set, which is the disk, falls in SC. And let's emphasize here how epsilon should behave. It should be a positive, right? So this symbol means there exists. In 2 dimensions, this guy right here would look like, a disk. In 3D, it's a ball or a sphere. In n dimensions, given a topology which, it consists of a set X and you start talking about a collection of subsets, it gets really more complicated. In 1D, it's an interval. When you say X, let's say X naught is 0. So once you say X is, an absolute value is less than 1, then you mean X is between -1 and 1, right? 2 dimensions, it is a disk of center X naught and radius epsilon. So yeah, if SC is open or a set is open, then its complement is closed. And as we said, it is possible for a set to be neither open nor closed. You can take a simple counterexample. The following set, X in R, such that X is between 0 and 1, excluding 0 and including 1. So this is called a half-closed interval, because you can see it contains the boundary 1, but it doesn't contain at 0. The complement would be, closed here and open here, everything greater than 1 but open, everything less than 0 but closed. It's also not closed and not open. So this is a counterexample of a set that is neither closed nor open. So yeah, the first property that we need is S to be closed. And the second property is that S should be solid. Now what does that mean? It simply means that the interior of your set S should not be empty. And every point within S, which is not on the boundary, is called an interior point. And we need that the set shouldn't be empty, because it happens that the empty set, if you come and think about it, it is an open set. And not just that, the empty set is both closed and open, right? So you can actually prove that the empty set, which is usually denoted as phi maybe, which means that the empty set, and also the complement, which is all the space, if we're talking in real numbers, R, is both closed and open. It's not something easy to digest, but it's both closed and open. So everything starts to get, I would say, a bit more interesting when we're talking in the, when stuff go to infinity or go to, 0. Everything at the limits is super interesting. So if you think about the set R, so if we're in 1D, so R is all, this real axis. So is it closed? Yes. And is it open? Yes. Because there's this duality. It's not comfortable when you come and think about it. It's really not comfortable because you're going to infinity and you want to check if it's closed. It turns out that it's both closed and open. Now, how can you prove that R is, both closed and open, or the same for phi? Well, let's start with phi. It's not that straightforward, but you can tweak around with counterexamples. So what I basically do is this when I get stuck. I try to find counterexamples that, guide me through a certain proof, for example. So you can define phi, you can play around with the empty set. There's infinite number of ways to define phi. You can define it as such. So it's all x's such that they fall in, if we're talking about the real set R, so it's all x's in R if we're in 1D, such that x falls in maybe 0, 1 intersection with, let's say, 2, 4. Because those two intervals have no intersection. They do not intersect, so the intersection is empty, therefore phi, right? Now, there's a property which tells you that the intersection of two open sets is open. This means that your phi is open. Proof is done. So really, this is how phi is open. And there's another, and using the definition of closed, since phi is open, then its complement should be closed. So phi complement is closed. And the complement turns out to be nothing other than R. So you just proved that phi is open and R is closed. Now, how do you prove phi is closed and R is open so that you prove actually that both phi and R are both closed and open? Well, so you define R as the union of two open sets, right? So the way you can define this is as follows. It's all x's, such that where x is greater than 1, union x less than 2. Why did I write it that way? It's so weird. It's so weird, like, I don't know why I did this. So we can like say that such that x is in the union of 1 infinity, union minus infinity till 2. We could define R as follows. So this is the red portion and open, so it's not including 2. And the blue portion would be everything from 1 till infinity. What can you say about the union of the red and the blue? It is R. It's all this axis going from minus infinity till infinity. Okay? Now, since it's the union of two open sets, then R is open. So its complement, which is phi, should be closed. And the proof is done. So we just proved that phi is both open and closed, and so is R. Now, going back to the solid thing right here, solid is a set where its interior is not empty. So why did I talk about phi and R? I don't want a set that is, just closed, because phi could be closed and is empty. Well, I don't want phi. So to exclude the phi, this is one way of telling you, hey, an interior should be non-empty. So everything that is not on the boundary should be non-empty. Okay, so one way to express this mathematically is to say that the interior set of S, int of S, which is the interior of S, is not phi. So a direct consequence from this would be if K is open, then naturally the int K is K. Because since K has no boundary, so it only contains interior points, therefore the interior set of K is K. Okay, so that's it for solid. Right, so now we need the fact that, or we need the property that S is pointed. And what does pointed mean? It means that if you grab a point in S such that its negative is also in S, then X has to be 0. And what that basically means is that S contains no line, okay? So if you grab a point and its inverse that both belong to S, it has to be the 0 vector, okay? Okay, going back to the set S, if our set S satisfies the three properties which are closed, solid, and pointed, and on top of that, if S is a convex cone, we can then say that S is a proper cone. All that to say that it's a proper cone. So if S is a proper cone, there's a lot of cool stuff we can do with S. One is you can go ahead and generalize inequalities that you know. So if your S is proper, then you can define something as follows. We say that we have a generalized inequality with respect to a proper cone S. We denote X is less than or equal to Y with respect to S. This is equivalent to say that my vector y minus x, or my point y minus x, belongs to S. As simple as that. Okay? And when you see a strict less than or equal to, it means that you belong everywhere except the boundaries, which means that also, since we're closed, means that you're in the interior of S. Okay? That's what it basically means. Now, this is called a generalized inequality. And we have really two famous generalized inequalities which are used so much that people sometimes forget this S. So one might say, oh, we have a less than sign, and it gets mixed up. But no, fear not. Fear not. In case we're talking about vectors, then you cannot say, oh, I have a vector less than a vector. And the same way of talking about numbers, right? No, it has to be with respect to some proper cone. And when it's dropped, it either means one of the following. So you have to ask, is it this? If not, then it's that. And what are those two? So one is pointwise inequality, and two, some people call it positive definiteness inequality, and some people call it, matrix inequality, because it's oriented towards matrices. It's dedicated to matrices. And what does each of those two mean? In each case, you have a different S, which is natural, right? So here, your S, which has to be a proper cone, or else we're not allowed to talk about generalized inequalities, it has to be R plus N. And what does that mean? It means the n-dimensional space, of positive entries, positive and real entries, right? Okay, so once you denote x less than or equal to in the sense of R plus N, Y means that Y minus X belongs to R plus N, which also means that Yi is greater than Xi for any I. And what does that mean? It means simply that, I'll give you an example. 2.4, 5.1, 7.9, and 10. You are allowed to say that this vector is greater than, in this sense, R plus N, any other vector where each component is less than the components here. Something less than 2.4 would be 2.3. Something less than 5.1 would be 5. Something less than 7.9 would be 7.8. And something less than 10 would be maybe 9, okay? If one entry does not respect this inequality, then you're no longer allowed to say this. Now, this has another consequence. This means that, in your real field, when you used to talk about numbers, you have one of the two. It's either x less than or equal to y or x greater than y. Either or. Well, this binary, sense does not work with generalized inequalities. We have some exception. Give me a bit of more time. We'll talk about that later. But for the meantime, just keep that in mind. And I'll give you an example. As simple as that. 1, 2, 3. Or why am I going to higher dimensions when I could talk about only 2 dimensions? And invert it. 2, 1. This, you cannot say that this is greater than this in an R plus N sense. Nor could you say that this is less than this in an R2 plus sense, right? This doesn't work and this doesn't work. And the reason is obvious. I do have 1 less than 2, but my 2 is greater than 1. So you cannot, place an inequality here. Right, so this is it for positive inequality. Now let's talk about positive definiteness inequality or matrix inequality. And what that means is that, previously in pointwise, you could see pointwise inequalities applied to vectors and matrix inequalities applied to matrices. Your S here would be, as we described previously, the set of all symmetric and positive semi-definite matrices. What that means, we used it previously when we said x is greater than y in a matrix sense, which means that if I say x is greater than or equal to a matrix y, both of them are of size n by n, right? Because we're in the space of n. In the sense of s plus n, this is equivalent to say that x minus y belongs to s plus n, which is also equivalent to say that x minus y is PSD, symmetric as well. You could have that, neither x is greater than y or y is greater than x. And what that means, as we said in pointwise inequality, when we gave this example right here, your generalized inequality is not a linear order. It could happen that you could pick 2 points such that the following and the following are both false. It could happen. When you find at least a couple, x, y, where this is not applied, then, you say that your generalized inequality is not a linear order. Okay? Now, since we defined generalized inequalities with respect to a proper cone, then we still have this notion of, a minimal and a maximal, point, since we're comparing in a sense. Otherwise, it wouldn't be called an inequality, right? So in that sense, we're comparing. And therefore, we could still capture the essence of what a minimum element of S is. So now, what does a minimum element mean? You need to do the distinction between minimum element and the minimal element. It's totally different. When we talk about minimum element, it means that you're allowed to say that a point x min is a minimal element, is, let's say, min, lm, just short for minimum element, min lm. Of course, with respect to the generalized inequality with respect to s, right? If for any other x, I pick not an s because s is a proper, cone, right? And, I define, the generalized inequality with respect to a proper cone, but my elements need not to come only from S. You get what I'm saying? So let me denote another set, which is C. So you can think about C as a certain given set, and you would like to find the minimum element of this set with respect to a proper cone. You need to do the distinction between S and C, okay? So going back to minimum element with respect to an inequality, how do you define a minimum element? Is simply, if you pick any x element in C, it has to be that x min is less than x with respect to S. So you cannot pick another element which is greater than x min in this sense, which means that x minus x min is in S. Is that clear? Okay, now this is what a minimum element is. You can also define a minimal element with respect to a set C as well. So let's denote this as MIL instead of MIN. So XMIL is a minimal element, of course, with respect to generalized inequality. And the minimal element is also defined for a set C, as in minimum elements, and we discussed that. If you pick any x in C such that your x is less than or equal to xmil, right? So if you happen to find another x, now this might sound weird, but it's okay. Yeah, if you pick another x which is less than your minimal element, then guess what? It has to be your minimal element. People might jump and say, whoa, wait a sec. It seems to me that it's like a minimum element. And, because if you pick something which is less than, it has to be in C and it has to be less than, sounds so bizarre, right? But there's an alternative definition to both minimum and minimal elements, which clear this definition out. But, sometimes it's useful to view it this way, but, both are equivalent. So another definition of minimum element is the following. X min is a min element, of course, with respect to S, if and only if you can prove that your C set, which you're finding the minimum element of, is a subset of what? X plus S. And what does that mean? X plus S. It's not that, you're adding, or because this is a vector and this is a set. Well, this is a set, which means that it is the set of all vectors that are greater than X. Simple as that. So this set right here is equivalent to saying all y's that are greater than X. This and this are equivalent. Well, if your C is contained or is a subset of this set, which are all the elements greater than X with respect to S, then X min is said to be a minimum element. Now an example right here would be the following. If I go ahead and restrict my S, so this is my X1 and this is my X2, right? And since we're talking about R2+, then we're in the first quadrant, right? So if I go ahead and shade it, it will look something like this, right? My C looks something like this for no reason, just for sake of argument. And it would be this region right here. If you want, we can close it as such, right? So this guy right here is my C, and the blue region is my S. The question is, what is the minimum element? Well, the minimum element here is your zero vector, your 0 point or 0 vector, whatever you want to call it. And why is that? You can use both definitions, but let's see it on the second one. Because your C falls totally inside what? Which set? X plus S. Therefore, the proof is done. So 0 is my minimum element, okay? Similarly, we have another alternative definition for minimal element, which has the same essence. So an alternative definition would be XMIL. Now, instead of saying X plus S, we'd say X mil minus S. Okay? So what is the criterion right here to say that X mil is a minimal element if the following is true? So this set intersecting C is a singleton set, which is X mil. Okay? So what does that mean? Similarly, when we said X min plus S is all points that are greater than X min in the S sense, right? In the you know, as we in the generalized inequality sense with respect to the proper cone S. So X mil minus S is also a set which are less than or equal to X mil, right? Yeah, it's all those points that are less than X mil. So if I were to define it alternatively, it would be all y's that are less than X mil with respect to S, of course. Right? So this and this are the same thing. Those two are the same. Okay? So if you grab all points that are less than X mil and you do an intersection with C, if this turns out to be X mil, then you can say that your X mil is the minimal element. And an example right here would be the following. So again, if we take our S to be R2 plus, so this is my S, and let's take our C to be something like this. So I'm going to pass a line here as such, and I don't care what happens there, like this, do this. Well, I do care, of course I do care. And if you want, you can close it. So yeah, this is your C, right? This guy is your C, okay? And I'm going to, pass it as such in the origin. Now the question is, does it have a minimal point? If so, what is it? So first of all, one might get the impression, oh, it is, maybe this point right here, because it's on the extreme left, or this point right here because it's the lowest, but it's neither this nor that. It's actually this point right here. The 0 again is your minimal element. And why is that? Well, let's try to shade the region which is defined by X mil minus S, which is 0 minus R2 plus, which is minus R2 plus, and therefore it would be everything, in this region. So everything in 1, 2, 3, the third quadrant. All those vectors of size 2 or points of size 2 that contain negative entries. So this is your xml minus s, right? And what is your c? It's the green area. Where do they intersect? They intersect at the blue point, which is your xmil. So by assumption, your xmil is 0. Okay? Now one might ask, oh, but what if I pick this point, this guy right here? Okay, let's try it. So if this guy right here is my xmil, then what is my xmil minus s? It's all points less than this point. In other words, they would be all elements lying in this red region, right? And now the question is the intersection of this red region and the green region only the red point? Yes, it is. So we have another minimal element. And guess what? It applies to all those points right here. All those points right here. On this line. All those elements are said to be minimal elements. So what does that mean? Your minimal element is not unique. So all those elements right here, I'm going to highlight them. This means that minimal elements are not unique. Now, you have other properties that guarantee a unique minimal element. It happens when, okay, I'm not going to go into details because that's not what I need right now. We're just giving some definite, but if your C happens to be a partially ordered set, means that you can compare all elements in it. And if you could find a minimum element, after that you could say, oh, I only have one minimal element. And to get a sense of what I'm saying, let's go back to this first example I gave here. Do I have a minimum element? Yes. What is it? It's the 0. Now, the question is, do I have a minimal element? Yes. What is it? It's only 0, which means that your minimal element is unique. And what is your S? It's R2 plus. So I forgot, we didn't define a partial order. So a partial order is not a linear order. You need to at least have an S, which is a partial order. And what a partial order is three things. Reflexivity, which basically means that for any x you choose in your S, then x is always less than or equal to x. Which means that x minus x is always in S. What is x minus x? It's 0, so S should always contain the 0 element, okay? 2, you need the antisymmetric property, which is simply the following. If for any couple xy, you have that x less than or equal to y and y less than or equal to x, so antisymmetry, then guess what? X is y, as your intuition might tell you, okay? And last but not least, the transitivity property. What that means is, okay, if you pick any a less than b and b less than c, then as intuition might tell you, a is less than c. If you have all three, then your S is said to be a partial order. Now going back to this example, is our S or the R2 plus a partial order? Yes, you can go ahead and verify. All three properties hold for this S, and therefore we can apply what I was previously saying, which is if your S or R2 plus is a partial order, and if you manage to find a minimum element, then your minimum element is also a minimal element and is unique. Again, this depends on your C as well. Here you have infinite number of minimal elements and no minimum element, because you cannot find a point which is contained inside this point plus S. It does not admit a minimum element. Now this is some cool stuff we can do with a proper cone. We can define, generalized inequality, minimum and minimal elements, and so forth. Right, so after we talked about generalized inequalities and stuff related to it, like minimal and minimum elements, we can now take a step forward and give some useful properties for generalized inequalities. Even though generalized inequalities generalize the inequality that me and you know, they still share really similar properties. So let's start with the first property, which is it preserves addition. It means that if I have a less than b, now I'm going to drop the k here, okay? I'm just going to drop it for just sake of presentation. So I'm going to denote less than the generalized inequality with respect to the proper cone k as this, and the less than or equal as this. So if a is less than b and c is less than d, then you can say a plus c is less than b plus d. Next, we have the transitive property. And what does that mean? It means that if a is less than b and b is less than c, then a is less than c. I'm not going to prove them here. They're really easy to prove. All you need is the definition. This inequality is also preserved under non-negative scaling. If I have a less than b, then if I grab any positive scalar or non-negative, then I could scale with no problem. Then alpha a is just less than alpha b. So far, so good. Those properties are also shared with the traditional inequalities that we know. We also have the reflexivity property, which is basically a is less than or equal to itself, right? You also have the antisymmetric property, which basically tells you that if a is less than b and b is less than or equal to a, then a has to be b. We also have that generalized inequalities preserve sequential limits. So what that means is that if I have a sequence of xi's and another sequence of yi's where xi is less than yi for all I don't know, it's an infinite sequence, so until infinity. And even more than that, we have that the limit of xi is x and the limit of yi is y, so this is the limit as I goes to infinity, and we have the inequality here, don't forget. Then what can we say? Then x is less than or equal to y. Means that if you have both limits where each entry of xi is less than its corresponding yi, then the limit of both sequences follow also the same sense of inequality, okay? So far we talked about the generalized inequality. We have some strict inequality properties which follow from the generalized inequalities, such as the following. If you have a strictly less than b, then you can say a is less than or equal to b, right? If a is less than b and c is less than or equal to d, then you can say that a plus c is strictly less than b plus d due to the gap between a and b. Okay, you've also got the scaling property for the strict inequality. So if a less than b and alpha is strictly positive, it has to be strictly positive as well, this alpha. You can go ahead and say alpha a is strictly less than alpha b. You know, because if alpha could be 0, then this doesn't work. The strict inequality doesn't work anymore, because for alpha 0, both of them are 0, and therefore we could relax this strict inequality to a 1 with equality. Even more, strict inequality does not satisfy reflexivity, so you can't say something like x is strictly less than x. This does not work, so this is false. And the last one would be if a is strictly less than b, then for small perturbation vectors, so mathematically for small u and v, you could say that a plus u is less than b plus v. Now, before we go ahead to the last section of this lecture, which is entitled Dual Inequalities, so there's also, as for generalized inequalities, there's something also called dual inequalities. Before we go ahead and define a dual inequality, we need to define a dual cone. What a dual cone is. In an analogous way, we defined a proper cone for a generalized inequality. We need to have a dual cone to define a dual inequality, right? So first of all, what is a dual cone? By the name dual, cone means it's a cone with respect to another cone. So let K be a cone. It's not necessarily a convex cone as we talked about here. A convex cone is simply a linear combination of the following form where the alphas are non-negative. So if I pick x1, x2 in the cone C, then the linear combination alpha 1 x1 plus alpha 2 x2 should fall again in C. So in that case, we can say our cone is convex. But if we're talking about any cone, it need not be convex. So how do you define a cone in general? If for any x you pick in k, then any scalar multiple of x should also fall inside the cone. So that is a cone in general. We should have defined it here, but we kept things consistent because all those examples were given for convex sets, right? So yeah, now the dual cone denoted by k star is the following set. So it's all y's such that x transpose y is positive where my x's come from k. So pick all your x's in k. It's the set y's such that the inner product with those x's are positive, okay? Now this set, you can prove it, it's always convex. No matter if k is convex or not, I don't care. So examples on dual cones would be the following. So if I have a subspace V, for example, V which is an Rn, and by the way, every subspace is a cone. So it makes sense to define a dual cone for the subspace. Then if we define V star as such, the dual cone, it is nothing other than its orthogonal complement. So denoted V perp or superscript perpendicular, which is all the y's that are orthogonal to all the vectors that come from V. Another example would be if I choose my cone K to be Rn plus, which is all vectors that have positive entries. This is a cone and it's convex. Then its dual cone is again R plus N. So this cone and its dual are the same. So if you're looking for its dual cone, well, it's itself. And why is that? If you write this definition, you want to pick all those vectors that you inner product them with all positive entries to be positive. Those entries should be again positive, because to guarantee positiveness, you should have all those entries as positive. Now, I know you have some counter examples where, such as 1, 2, 3 positive entries, so it belongs to R3 plus. And if you come and inner product it with, I don't know, the vector minus 1, 2, 3, you will get minus 1 plus 2 times 2 plus 3 times 3, which is positive. Then one might say, oh, but this vector belongs to k star, right? But no, it should be all y's. So if you grab a y, which is this vector, you should inner product them with all vectors coming from Rn plus that yield positive entries, so that you say that this y comes from k star. It has to work for all x's that come from Rn plus. A counter example where this y fails is simply by setting this 2 and 3 to zeros. You would get minus 1, which is negative. Hence, this guy doesn't fall in k star. Moral of the story, Rn plus is its own dual. Another example would be what is the dual cone of the PSD cone. In case you forgot what that was, it is all symmetric matrices that are positive semi-definite. Okay, this is a cone and it's called a positive semi-definite cone. If this is with strict equality, it's positive definite cone, else it's positive semi-definite cone. Now, the question is, what is the dual cone of the PSD cone? So, what is K star? So if we write the definition, K star is all y's such that, in that case, we would have matrices, right? So instead of vectors as such, we should write a matrix, because the dual cone of a matrix would be another set of matrices. So it's all y's such that, and to be able to say something that is positive, we can't say all x transpose y positive, because x transpose y would be a matrix. So instead, the inner product between matrices is usually, there's multiple inner products between matrices, but usually people use the standard one, which is the trace. We can drop the transpose because it's symmetric. X transpose is x, right? So when the trace of xy is positive, this is the criterion of positiveness. Now the question is, what are all such matrices y's that satisfy This for all x's in Sn plus. It is also again Sn plus. Well, it's simple. This could be proved by, so if this is k star, you can prove it using the following logic. If you want to prove that k star is indeed k, then all you have to do is prove the following. If you pick a y not in k, then it should not be in k star. And if you choose a y in k, then it has to be in k star. So you have to prove both statements. Let's start by picking y not in k, or equivalently y is not in Sn plus. And what does that mean? According to the definition of positive definiteness, it means that there is a vector z such that z transpose yz is negative. Let's introduce the trace on both sides. The trace is a linear operator. So z transpose yz is less than trace of 0, which is 0. Now, using trace AB is equal to trace BA, or we can move this Z here, right? It's a circular thing, so we get Z transpose Y negative. We have this. This exists for some Z. I don't know which Z, but at least I know it exists, and it's not the 0 vector. Now, what does that mean? If you pick this to be your X, i.e. X is ZZ transpose, and any matrix of this form is in Sn plus, by the way, because it is an outer product, and all outer products are positive semi-definite matrices. You can easily prove that. This is an X that falls in Sn plus. And guess what? This type of Y has violated this criterion. So Y does not fall in K star. This means that Y will not fall in Sn plus star. 1 is done. Now 2, we have to prove the complement, which is if we pick our y in k, i.e. if we pick our y in Sn plus, it has to fall in Sn plus star. So we have to prove that trace x, y is positive for all x's in Sn plus, right? And how do we do that? Given that y is in Sn plus, so let's write it down. Trace xy is equal to trace. If we express y as, now here goes y, and we will plug in its eigenvalue representation, summation of lambda I, vi transpose, where lambda i's are its eigenvalues and its corresponding eigenvectors are denoted as vi. Now, since y is in Sn plus by assumption, then all our lambda i's are positive. We are sure of that. Now, continuing this, we could insert x inside the summation, right? And even more, since trace is linear, we could introduce it inside. Now, using again the circular property of the trace, I could move my vi here, and I will have, now since this is a scalar, I could omit my trace, right? So I will end up with something like this. Now, look at this term right here. It is a sum of n positive entries, because lambda I is positive, and vi transpose x vi is also positive because x comes from Sn plus. So by definition, this term is also positive. So what is a product of two positive numbers? It's also positive. Therefore, the sum of n positive terms is positive. So going back right here, we can say that the trace of xy is positive, hence y falls in Sn plus star. Statement 2 is proved, statement 1 is proved. This means k is k star, and therefore Sn plus is Sn plus star. And the proof is done. So cones would be the following. K star is always, as we said, convex / closed. And 2, if a cone falls inside another cone or is a subset of another cone, this might lead you to think that K1 star is contained in K2 star, but it's the total opposite. It's K2 star falls inside K1 star. And 3, if the cone K has a non-empty interior, then guess what? K star is pointed. If the closure of K is pointed, then K star has a non-empty interior. And last but not least, the dual of the dual is not necessarily K, it is the closure of K, or even more, the closure of the convex hull of K. Property 6, so if K happens to be proper, then K star is also a proper cone. So if you can define a generalized inequality on K, then you can do so on K star. And even more than that, making use of property 5, we could also say the dual of the dual is the self. So it returns you back to the initial cone. So making use of property 6 right here, we can say that if I pick a proper cone K, then I can define a generalized inequality on K. Now, the dual inequality, or more formally, the dual generalized inequality, but for short, we call it dual inequality, is nothing other than the inequality induced on K star, the dual of K. Because we are sure that K star is proper due to property 6. So that is typically what a dual inequality is. And some of its important properties are the following. If x is less than or equal to y on K, this is equivalent to saying lambda transpose x is less than or equal to lambda transpose y for all lambdas that are positive with respect to K star. You see the equivalence? So if x is less than y, then if you inner product on both sides with the same vector and you preserve the inequality, then this vector is positive in the K star sense. And 2, so to exclude the equality, to exclude the zero vector. Now, since the dual of the dual is back to the self, the dual inequality, you could actually swap those definitions. So you can actually come and tell me and replace this K by K star and this K star by K. So the min LM that we talked about previously over here. So the min LM, if X min is a minimum element of a set of C with respect to the inequality on K, this statement is equivalent to saying that X min is the unique minimizer of lambda transpose Z for all lambda positive with respect to the dual. Now, of course, this minimization over here should happen on C to make sense that it's a minimum element of C. We have a property to say. So if X minimizes the same objective function here, lambda transpose Z on C for some lambdas positive on K star, then X is minimal. And that's typically it. That's it for this lecture. We covered a lot of topics that have to do with convex sets, starting with affine sets, then convex sets. We generalized convex combinations. We went ahead and gave a lot of examples on convex sets. We talked about operations on sets that preserve convexity. We also gave some applications of convex sets, more specifically on generalized inequalities, which is defined with respect to a proper cone that has to be convex, of course, because that's one of its properties right here. We also stated few famous properties of generalized inequalities, talked about dual cones, and defined what dual inequalities are with some of its properties. That's it for this lecture. In the next one, we'll be talking about more exciting stuff where we will cover all important stuff related to convex functions. Okay, I'll see you then.